Hello and welcome to this screencast where I'll be talking about the main ideas of section 5.3 of active calculus, which is on integration by substitution. First, I want to talk about a new piece of notation that this section introduces, and that's the idea of an indefinite integral. And so previously we've been looking at definite integrals, and they look like this. This was a definite integral, and that this results in a number. Okay, it's the net signed area between the graph of y equals f of x and the x-axis from x equals a to x equals b. Right. So this is I like to think about this as a net signed area. On the other hand, this notation here, where notice there are no more limits of integration, we just write the integral sign and then the function, means we want to find the most general antiderivative for the function f of x. So just like when we were talking about derivatives and we talked about the difference between dy dx, which was the actual derivative of something, and d dx, which was a command to take the derivative. This is really, I view it more as a command saying, find the most general antiderivative for this function. And by the most general, remember this is the context where we need a plus c on the end to account for the fact that any two antiderivatives are going to differ by a constant, and without more information, you won't know what that constant is. Okay, so we'll get some practice with that in another video. But let's start out here by looking at the special case of integration by substitution. And this one comes from our first special case of the chain rule that we saw, which is when the inner function was a linear function, right? And so we saw, and here I want big F to be a differentiable function and its derivative to be little f, then the chain rule says that the derivative of this is, well, in longer terms, we would say it's f prime of ax plus b times d dx of ax plus b. But we said f prime, big F prime was little f, and so we have that form, and d dx of ax plus b is just a. So that was the first form of the chain rule we saw, and it's going to be the first and one of the most common forms of substitution that you'll be using. And we want to be so conversant in using this that we don't even really have to think about it as a substitution. And so now here I have taken little f to be a continuous function. Big F is some known algebraic antiderivative. So I mean not one of those goofy integral functions that we were studying in section 5.1 and 5.2, but something like the fact that x squared divided by 2 is an antiderivative for the function x, right? An algebraic antiderivative. Then, if we want to do the indefinite integral of f of ax plus b with respect to x, then that's just 1 over a times big F of ax plus b plus our constant of integration, we call it. And that comes about by just rearranging this statement that we have up here, dividing off the a. So we're looking at 1 over a d dx f of ax plus b equals little f of ax plus b. And so any sort of statement like this that we have about a derivative can be translated into a statement about indefinite integrals, saying if we look at the indefinite integral of this, then we can get rid of the d dx, because we're saying give me an antiderivative for this function. Well, an antiderivative for the derivative of this thing in here is this thing in here. In more generality, we can look at the full form of the chain rule and undoing it. That's really what integration by substitution is. It's a method to undo the chain rule. So remember the chain rule. If we have two differentiable functions, f and g, we can differentiate f of g of x and say that's derivative of the outside guy, f, evaluated at the inside guy, g, times the derivative of the inside guy, or g prime. So we can just make a very direct translation of that statement, as we did on the previous slide, into a statement about indefinite integrals by sort of integrating both sides, recognizing that in the context of indefinite integrals, the integral sign and the ddx will negate each other or have opposite effects at the expense of adding this constant that disappeared when we took the derivative. The way we do this in practice is we tend to come in here, and so we look at something like this, and I'm going to let u equal g of x, and then we the way we work with this symbolically with differentials is we say du is g prime of x dx. And so then I look here and I see a g prime of x dx, and I turn that into a du, and I see a g of x here, and I turn that into a u. And now I look at this and say, oh, I need an antiderivative for this function f prime of u with respect to u. Well, we know that this is the derivative of f, so we're assuming we have some algebraic antiderivative f for f prime, and so we have f of u plus c, but we knew that u, right here, u was equal to g of x, and so we replace that and we get over here. And in our future screencasts, we'll talk more carefully about some specific examples so we can really see this integration method concretely in action.